Hello and welcome to this video where we're going to go over how to get started on these two homework problems, which are math-based problems for astronomy. In the first one, we're going to be dealing with different portions of Earth, and in the second problem, we're going to be dealing with the likelihood of being struck by an asteroid or at least experiencing one. Okay, so in the first problem, we are told some information about Earth, and there's some clarifications here that I want to point out. One is that we are told that the diameter of the Earth, which is excluding the atmosphere. So this would be the diameter from the center of the Earth up till the surface of the Earth, so the solid Earth, which is where the atmosphere starts. We're also given the total mass of Earth, which does include the atmosphere, although you'll find that the atmosphere, it has such a low mass that it actually would not show up within the three significant figures of the mass of Earth, 5.98 times 10 to the 24 kilograms. But regardless, that we're assuming that does include the atmosphere. So how do we go about solving this problem? Well, all parts of the problem, A, B, C, and D, and including the summary in part E, all involve the same approach, which is finding the mass of one portion of the Earth and comparing that to the total mass of the Earth. So let's take a look. In the first part, we're told that the density of the atmosphere is 1 kilogram per cubic meter, which is not very dense because, of course, it's a gas and it's not very dense. And we're told that it extends to a height of 100 kilometers above the surface of the Earth. Okay? And then in part B, we're asked about the crust, given the density of the crust, 2,700 kilograms per cubic meter, so 2,700 times denser than the atmosphere. Of course, it's a rock. Of course, it's much denser than air. And we're told that it has a thickness of 70 kilometers, so it extends from the surface down 70. After that, we're asked about the mantle. The mantle goes from 70 down to a depth of 2,900. And then from there, we're finally asked about the core. The core starts at that depth of 2,900 and goes all the way to the center. And if you subtract the radius of the Earth, which is half the diameter, and then if you subtract the 2,900 from half the diameter, you get this value right here, which is the radius of the sphere, which is the core. So if you stripped away the rest of the planet and just the core was left, you would have a radius of 3,478 kilometers. So a significant portion in terms of the radius, but of course a much smaller portion in terms of the volume because it is, after all, just the center of a sphere. Okay, so the picture hopefully shows all these different layers of Earth, like layers of an onion, just not equally spaced. All right, so let's take a look at the approach to solving this problem. So in each case, you are concerned with primarily the formula for the volume of a sphere. So if we were, say, finding the total volume of Earth, it would be 4/3 pi r cubed, where r was the radius of Earth, again, half the diameter. But except for the time we do the core, we actually don't exactly care about a sphere. Instead, we care about the difference between two spheres. So consider that we just want to find the volume of the atmosphere. Well, the volume of the atmosphere would be the volume of an outer sphere that includes the atmosphere minus the volume of an inner sphere that excludes the atmosphere. That way, we would just be finding this volume, which is the volume of a spherical shell. Okay, so that formula is just the 4/3 pi, and then the outer radius cubed minus the inner radius cubed. Okay. By the way, notice it's not the difference between the radiuses cubed. It's both of them cubed, one minus the other. Okay. So you'll use this formula to find the volume of a spherical shell. You're going to use that for the atmosphere. You're going to use that for the crust. Or you're going to use it for the mantle. Same approach. Okay. So for example, for the atmosphere in part A, well, the numbers, the outer radius would be the radius of the Earth up till the ground from the center, which is 6,378 kilometers. I got that number by just dividing the given diameter by 2. And then we'd add the 100 kilometers because that would represent the top of the atmosphere. Okay. By the way, the atmosphere doesn't just end at some particular height. It gets thinner and thinner, but this is often a value that's given as an approximate height of the atmosphere. The inner radius of the atmosphere would just be the outer radius of the planet. So 6,378. Okay. So those are the two numbers that you would use for R out, which you'd make sure to cube, and R in, again cubed. All right, and then take the difference between those cubes, multiply them by 4/3 pi. Okay, so that will give you the volume of the spherical shell, which is Earth's atmosphere. And then finally, since you need to find its mass, you would then remember that mass, by definition, is density times volume. Well, you know volume, and you're given the density. In the case of the atmosphere, it's 1 kilogram per cubic meter. Now, your volume is going to be in cubic kilometers unless you convert. And you definitely want to convert because otherwise you're going to have a mix of units here. You're going to have a density in kilograms per cubic meter, and you're going to have a volume in cubic kilometers. Totally different units. So make sure to convert, basically multiply all these numbers by 1,000 before you plug them in, before you cube them. That way your volume will be in cubic meters. In formula, or as variables, right? Instead of words, it's m for mass equals rho for density times v for volume. Okay, and then one of the last things that you're asked to do in throughout this problem is then to take a ratio. So then we'd want to find the ratio of masses. So if we look at the wording for part A, for example, I ask, what is the percentage of the total mass of Earth that is the atmosphere? So in that case, your ratio would be the mass of the atmosphere over the total mass of the Earth. Okay? Now the total mass of the Earth is, of course, given, right? This is the number that we'll repeatedly refer to. Every time we refer to the total mass, is always going to be this 5.98 times 10 to the 24 kilograms. All right, and so then you multiply that by 100, and that will give you the percent. Okay? This is the percent of Earth that is atmosphere. Okay? Specifically, not volume, by the way. We could actually take a totally different ratio in terms of volume. It would just be the volume of the outer of the spherical shell over the total volume of Earth. But that's not what we're interested in. Not what I asked for. Instead, I asked for a percentage of mass. So that's the calculation there, and it should be a tiny number because the atmosphere, first of all, is not that much of the total volume. It's significant, but not that much. And then when you consider that its density is so much less than any other solid part of the planet, well, that's where the mass just becomes insignificantly small. So the mass you calculate for the atmosphere will be tiny and will be a tiny percent of the overall mass of the planet. Not so once you get to the other parts of the problem. Part B, for example, the crust is a small overall percentage, but measurable. The mantle should be most of the planet, and then the core will be, well, also a large percentage of the overall planet, but not most. I do also ask you to represent this information in a table in part F. So you're going to summarize all of your results, but overall it's the same approach, just with some slight variations. Okay, so hopefully that's enough to get you started on problem 1. What's going on with problem 2? Well, problem 2 is all about interpreting this graph here and answering some questions. So for example, we're told to estimate the probability that a person who lives 90 years will be alive when an asteroid with a 90-meter diameter impacts the Earth. And then what is the probability that the same person is alive when an asteroid impact releases an equivalent to 10 to the 6 megatons of TNT? So this is all information you're going to get off of the graph. So let's go ahead and pull up some information on this. There we go. All right. So I just want to refer to this graph here because this has a bit more of the details that I was talking about previously in a class meeting. So what's going on? Why are all these things circled? And what's going on with all these green lines and blue lines? Well, the two parts we're asked about is the 90 and the one that's equivalent to 10 to the 6 megatons. So that means that this vertical line is the 90-meter diameter asteroid. So that's the one that we asked about in part A. And then this other vertical line over here is the one you asked about for part B, because you can see it corresponds to 10 to the 6 megatons of TNT, all right, which is a unit of energy. Now, the one in between, by the way, was just an example calculation, not one that you asked about in the problem. Now, this particular graph is difficult to read because it's what's called a log-log scale, right, which is a very helpful type of graph, but takes some getting used to, because essentially the numbers are not evenly distributed. They end up being spaced differently once we get to the next step in the logarithm. You can see that here with these vertical lines. So for example, here, each major line is a difference of a power of 10, just like in your table, just like in this table of impact frequency. And then but if we are exactly halfway in the middle, or somewhere halfway in the middle, this would not be 0.05, which is, a linear halfway between 0.01 and 0.1. Instead, we can see is actually 0.02, much less than half. And that's because, we go from 0.02, or actually this would be 0.03. So we have 0.02 here, we have 0.03, 4, 5, 6, 7, 8, 9, 10. So you can see they get much more spaced together, much more clustered together. So with that, I have estimated the following values for part A and for part B in terms of the impact interval, the amount of time between impacts. And I'm just reading that off from this horizontal line. So for part A, the impact interval would be 750 years. And that's just because of the intercept with the vertical line to the black line, which is the actual data, and then just connecting that over to frequency or going over to the right-hand side to get interval, okay? Likewise, for part B, if we continue over from the intercept, we find an interval of about 20 million years. So these are the intervals you should use for the purpose of calculation. Now, what actually is the calculation? Because you're asked, for example, in part A to estimate the probability that this person who lives for this amount of time of 90 years will be just present on Earth when this 90-meter impact occurs, right? How likely is it that this person is going to hear about this impact that's going to happen somewhere on Earth, anywhere? It could hit the ocean and be of very little interest, or maybe it would be a noticeable impact somewhere on a landmass. Because this would be a quite noticeable impact and could cause significant damage just depending on where it hits, okay? So if you take a look at the example, not one that you're asked to do in the homework, but just for the sake of showing the steps, let's consider the probability of a 400-meter asteroid strike, which is this middle vertical blue line, okay? And we want to find the probability of happening in a time period of 90 years, okay? Well, if we read off from the table, we see that the frequency for that 400-meter impact is equivalent to a interval, or would happen every period of about 50,000 years. So there should be a 400-meter asteroid strike every 50,000 years. And now we're going to assume that there's a 100% probability it will happen within that time period. So now we just need to find out what portion is 90 years of that much longer 50,000 years. Okay, so we set up a direct proportionality between the two, between the probability, all right, that we want to find, the 100% probability, which we represent as 1, and then the two time periods, the 50,000 years where the impact is sure to happen, and the 90 years where it may happen. And we find out that the probability of the impact happening within any given 90-meter period is just 0.18%. Less than 1%, about a fifth of 1%. So a small probability that this person will be alive when a 400-meter asteroid strike hits somewhere on Earth. Of course, there'll be a higher probability for the smaller 90-meter asteroid that you asked for in part A, and then a likewise smaller probability for the bigger asteroid, because probabilities go down as asteroid size goes up. Those are rare events for the really big asteroids to strike. All right, so you're going to take that same approach for A and B. And then also for C, where you're actually going to, well, C is a bit different. For C, all right, a little correction there, it should be C, not D. Here you're asked to find the probability that a person is struck by an asteroid. In this case, all you need to do is look at the type of asteroid that's given, which is the smallest one, the 4-meter asteroid, which conveniently happens once every year, all right? So on average, there is going to be a 1-meter asteroid hitting somewhere on Earth every year, okay? And this would be for part C, okay? So there's always, we can say that on average, there's a 100% chance that there's one of these 4-meter asteroids hitting on Earth, okay? Now, we're going to assume that this asteroid would be deadly, of course, very unfortunate, but deadly to a person that is struck by it. And we're defining being struck by the asteroid as being within a 5-meter by 5-meter square where the asteroid is hitting. So if you're within that area, then that is the deadly zone where the asteroid would kill you, okay? So that would be 25 square meters, or 5 by 5 meters, just a square. So the idea then is you're going to find the portion that square is of the overall surface of Earth using the formula for the surface of a sphere, 4 pi r squared, and then considering that the person is equally likely to be anywhere on Earth, which is a bit of a stretch. Of course, the person is not equally likely to be anywhere on Earth. They're more likely to be on land than on the ocean, but we're going to assume they are equally likely to be anywhere. So then we're just going to take the area over the area of danger over the overall area of the Earth, multiplied by the frequency that asteroid is going to occur per year, multiplied by the number of years the person is alive, and that's their chance of being killed by a 4-meter asteroid within their 90-year lifespan. So, in other words, let me summarize that. All right. So I want to just summarize this idea of taking the probability and extending it a bit more, because obviously all we were doing in parts A, B, and C was just comparing the probability over time, but now we've included this area, okay? So the probability would be the 25 square meters, okay, over the entire surface area of the planet, okay, that's that formula for the surface area of a sphere, times the probability per year, all right, which you know, we just mentioned it, it's 1, okay, because it should be 1 per year, times the number of years that the person is alive. All right, in this case, you're going to have a 90-year person, or a 90-year living person, so that's a chance. Each year, they have a certain chance of being struck by the asteroid. Every year they live, that there's a greater chance, but you still should get a tiny number because, as you know, this is not a likely way to die. Okay, but it'll be interesting to calculate the number. Hopefully, you see the approach, and it seems like a fun number to calculate. And by the way, that was C, not B. Okay, all right. So this will give you a good start on both homework problems 1 and 2. Thank you so much for watching this video. Bye for now.